It's time for the Chip Spotlight!
Welcome to the first ever Chip Spotlight, a show where no chip gets left behind. On today's episode, we look at the mighty 74HC595, a shift register to end all shift registers. Let's look at the basic specs. The chip contains two 8-bit register banks, the first set up to act as a shift register, taking in fresh data through a serial input pin. The second bank is set up for parallel loading and parallel output. The output of the first bank acts as the input for the second bank. This makes the chip very useful for serial to parallel conversion. There are two clock inputs to the chip, one to trigger each bank of registers. The chip can operate at both CMOS and TTL levels. There is also an output enable. This gives the chip the ability to work well on bidirectional data buses. The outputs can be enabled when writing to the bus is required and put into a high impedance state when reading from the bus is required. Another chip, perhaps coming in a future video, will be required to read from the bus. Also, the outputs are capable of sourcing up to 35 mA. A great use for this chip is for output expansion, especially in the case of driving screens. In the case where there is spare program memory but a shortage of output pins, then a shift register like this could be used to resolve the problem. The downside being that more program memory will be required to facilitate the outputs. There will also be a slight switching speed penalty. Another great use for this kind of chip is to generate address lines for larger chips when using smaller microcontrollers. This SRAM chip has a 16-bit address bus, too much for an Arduino Uno to interface with, but using two 74HC595s, the 16-bit interface can be reduced to only 5 pins. Let's look at this chip in action. Here, an Arduino Uno is being used to drive the 595. It takes a total of 5 digital pins to gain the full functionality of the chip. In some scenarios where the high impedance output state is not required, the output enable can be fixed to ground, reducing the requirements on the Arduino. The 595 has 8 LEDs connected to the 8 outputs of the second register bank. Now looking at the software, creating a class to represent the presence of the shift register allows the creation of an Arduino-like interface. The base function on which all other functions can be built from is this write byte function. This function takes a single byte and shifts it into the register, one bit at a time, starting at the most significant bit. With the write byte function working properly, a pin write function can now be defined. This function works to only change the state of one of the 8 outputs. To do this, the function must respect what the other pins are set to. To accomplish this, a byte is stored in the class that represents the current output states. This byte is modified by the pin write function, and then the write byte function is called on the updated byte. Bitwise operations are used by the pin write function to update the current output byte. The Arduino file simply uses the 595 to count at a very high speed, first counting up, and then counting down using the byte write function, and then scanning through all the pins using the pin write function. So that's it for the first episode of the Chip Spotlight. If you have any comments or suggestions, please leave them in the comment section below. Thanks for watching, and I'll see you next time.